of Talk Math with your friends. Today, it is my pleasure to introduce today's speaker, Benjamin Dickman. He is a K-12 teacher at a girls' day school in New York City, and he will be talking to us about proofs of divisibility. So please join me in welcoming Benjamin.
Hi, everybody. Thanks to you all for platforming me. I think it's meaningful that a group of university-based mathematicians thought it would be reasonable to let a K-12 teacher speak. I think that speaks well to your mission, irrespective of if this is a flaw. Anyway, I don't prepare talks in advance. I have a few notes that you'll see momentarily. But since you gave me this platform at the moment, let me just put out a plug for what's called lathisms. And I'm going to use a 1 instead of an I for their name. This is a nice organization. If you use Twitter, my handle is just my name, Benjamin Dickman, and I have pinned right now a recent tweet from them. They're trying to raise money to incorporate as a nonprofit. There is no compensation that I know of for this talk, and I don't think any of you were charged a gate fee, so maybe that would be a good place to look. If not to give money, 500 cents or $500, either way. Then maybe you can just retweet it or something. Okay. I'm about to scroll down in this page, and there is going to be part of a math overflow query that is visible. I'm asking you not to Google it. I know some of you will see it and wonder what is contained in this math overflow question and answer page. It will ruin part of the talk. If you can prevent yourself from doing that, that would be great. If you do not know what Math Overflow is, it's a question and answer site for research mathematicians, and it's not always the most pleasant place. It suffers from some of the same problems that the larger mathematical community suffers from. That said, here is the question: elementary plus short plus useful. And I tried to blank out the names as best as I could so that nobody's put on blast, but I missed one. It is what it is. So asked 9 years and 10 months ago, so almost 10 years ago. It says, imagine yourself in front of a class of very good undergraduates who plan to do math professionally in the future, whatever that means. You have 30 minutes. After that, you do not see these students ever again, whatever that means as well. And you need to present a theorem which would be 100% useful for them. What would you do? And so I have in here some of the sample answers that were given by other users of Math Overflow. So if someone says the Banach fixed point theorem, then there's singular value decomposition. And then a professor of mathematics says, +1, because even I don't know what that is. Okay, I'm not clear on that. Picard-Lindelof theorem on existence and uniqueness of solutions to ordinary differential equations, introducing Picard iteration along the way. Again, this is a one-time 30-minute talk for undergraduates. So I don't know, these are some of the higher voted answers. A theorem that just links to its Wikipedia page. And then this isn't one of the highest rated ones, but it was one of the first answers that was given, which is compactness of first order logic. And just to be clear, they mean using ultra products, not as a corollary of completeness. So that's their plan for the 30 minutes to get undergraduates you'll never see again to commit to a lifetime in mathematical research. So in part, this talk is a response to that very nice question, I think, which is to find a theorem for 30 minutes. And I'm quite dissatisfied with the answers that you can see excerpted here. This is the last pre-prepared piece that I have, which is apparently what I said I was going to talk about. So this is to keep me honest. It says I'm going to talk about proving things in multiple ways, what a statement about divisibility. And I said that I would do it 7 proofs. We'll see about that. Okay. And commentaries. Okay. And then something about generalization. Fine. The other part of this talk is that it's a response to some of the math talks that I've seen where people seem to delight in having everyone get lost within maybe the first 10 minutes. It's like 5 minutes for specialists, and then the next 5 minutes is to get people lost, and then 50 minutes or whatever of nonsense. I cannot understand why this is accepted in the mathematical community. I don't think it's quirky or absent-minded. I think it's just mean. So my goal is to be speaking in a way that is understandable to everyone for the duration of this talk, which means if you do not understand something at any point, jump in. I'm not monitoring the chat at all, but feel free to interrupt me. The concern that I have is that people might see where I'm going with some of my comments. And so I would also ask that you don't jump ahead by interjecting with a punchline if you have one in mind. So this is not a talk whose goal is to have you confused in abstract nonsense. And also, if you think of something before it's come up, maybe just like write it down on a piece of paper. You don't need to shout it out or put it in the chat. That would be great. So, okay, here's the theorem. I will not use the full allotted time unless it's necessary, and maybe it will be. So, okay, the theorem. Theorem. I think this is how many math talks start, right? Theorem. The theorem is that n squared minus n is even. And I hope that I can prove this within the allotted time. It's already 3:38, so okay. You're probably wondering for which n, so I mean specifically for positive integers. This is the most technical thing I may write today for all n in z plus, which is to say all natural numbers or all positive integers. I don't want to get into whether zeros counted or not. Here I mean the numbers 1, 2, 3, 4, and the other numbers you can get by adding 1 a finite number of times. And I hear this frequent complaint that there are not enough examples. Let me give you an example. Example, like if n is the positive integer 45, this would be saying that 45 squared minus 45 is even. And I think this is probably true. Hopefully it is, right? 45 squared is 1025. And if we subtract 45 from that, you get 1980, right? The reason I know 45 squared is like similar to all of you. I wondered whether I would get the opportunity to live through a square year in my life. And I see that 2025 is coming up soon. So 1980 is an even number. And maybe I'll put in another one more side note. I saw some discussion when this year first started among the many important events of 2021. People were asking whether 2021 is a prime number. And 2021 is equal to 2025 minus 4. And what I've written is a bit different than what I said. But if you see this as a difference of squares, it's 45 minus 2 times 45 plus 2. So it is 9. It is not prime. Next year is going to be even. 2023 is 77 short of 2100. So it's not prime. 24 no good. Then there's a 5. I think 6. I think 2027 will be the next prime year. So we gotta wait. Anyway, let's prove this theorem. I'm gonna write a heading and then I'm gonna kick this out to y'all to try to prove. This is your chance to jump in. If you're a person who doesn't usually jump in, I mean you. And if that describes you, you probably just thought, oh, he means me, but I'm not gonna do it. I know, I actually do mean you. So okay, here's the first method. The question is about evenness and oddness. So let's prove it using evenness and oddness. Does anyone have a suggestion for how we might proceed using evenness / oddness?
Well, I know that an odd number squared is still odd, right?
Okay, so you're tackling the odd case first. I wrote evenness / oddness and you're doing the second part. Oh, fine. Okay, odd squared. And you're saying this is still odd, okay. Yeah, you want to finish off the odd part? Maybe someone else will do the even part?
Sure, and then you subtract off an odd.
Right.
So you get with an odd minus an odd, and that'll always be even.
Right.
And I bet I could push 2's around if I really wanted to be more careful.
Yeah, right. There's a version of this where maybe it's an introductory class on proofwriting, and maybe you want to actually write things out with symbols. I don't really care to. Maybe I'll write a little bit out so you know what I mean in case it's not clear. The version would be something like, let n be an arbitrary odd integer. Then it can be represented in the form 2k plus 1 for some integer k, and 2k plus 1 squared minus 2k plus 1, something. It would head somewhere. I don't think we need to do that today. Yeah, odd squared minus odd gives you even. Notice that for what it's worth, I didn't write an equal sign. I put in an arrow. I try to avoid abuses of the equal sign. And I'll mention why in a moment, but does someone want to talk us through the even case? I don't have the same access to teacher wait time that I would in a classroom. So I will just forge ahead relentlessly unless somebody wants to jump in. Does someone want to talk us through the even case?
Paige is smirking at us. Paige, would you like to walk us through the even case?
But Tian just unmuted, so I feel like
Perfect.
priority, you know.
Yeah, so analogously, if you take an even squared, that's also even. And then you subtract the same even value. And presumably, we know at some point that sums or differences of evens is also even.
Yeah, right. So in some sense, like maybe the talk is over, right? Because we proved it. This does prove the entire proposition. The odd case and the even case does cover all of the counting numbers. Again, I use the arrow, not an equal sign. I think there's a small chance that someone would say, oh, even squared minus even equals even. Maybe even is the same number all the way through and say, well, what's the first even? I don't know, maybe it's 0. 0 squared minus 0 equals 0. Oh, that's true. And I say, no, I'm positive. And they say, okay, so 2 squared minus 2 equals 2. And I thought, oh no, that's like we've lost the thread. Anyway, the promise here was actually to do 7 proofs. So yeah, that's 1. Okay, here's the second one with its title. The second one's called factoring. And this is pretty common when you see algebraic expressions like n squared minus n. Does anyone have an idea about how we might factor it to prove that it's even?
Could we just factor out the n?
Yeah, factor out the n. I don't know whether you mean on the right or the left. I'll factor it on the right. Fun.
Either way.
And then how does this, I mean, this is true. It is true that these two things are equal, but how does this prove that it's even?
Then I would say that either n or n minus 1 is even.
Okay.
And either way, I gotcha.
One of these is even. Either way. Now, what do I write? I gotcha or you gotcha? Gotcha.
You can get me.
Yeah, okay, gotcha. Yeah, right. If you have 2 integers in a row, in this case, 2 non-negative integers, right? Not necessarily positive, because if n were 1, it'd be 0 times 1. Anyway, if you have 2 integers consecutive, one of them's got to be even, so their product is even. Yeah, many proofs end with gotcha, right? We already have 2 proofs. I hope you're convinced that this statement is true. Okay, the third one, geometric. This happens if you teach high school all the time. People say, did you know that there's an algebraic representation and a geometric representation? Oh, okay. All right, well, what is it here? Does anyone have an idea about how to represent n squared? How would you do that?
With a square.
Yeah, I would draw a square.
It's a good idea. And then we got to do the n squared minus n, right? So let me write that down to remind us. So I'm going to draw a square. Maybe you can do them with dots. You can do them with like an array of little squares, but I'll do dots. I think that probably doing a 5 by 5 square is the limit of my patience. And so that's what we got here. And then the question I have, if this really does represent the n squared, how are we going to geometrically represent subtracting n? Anyone have an idea?
You subtract 1 column or 1 row.
Yes, idea. Should I switch the colors, you think? How do you draw an idea? Maybe like this. Oh, it did not switch colors. Well, too bad. Okay, idea. Remove a column or row. Yeah, this will work. If you analyze what happens in this case, you remove 1 column or remove 1 row, you actually end up in either the first case or the second case, in some sense, if you look back to our earlier proofs. Maybe the second one, the factoring one, is more clear. Like this is n squared minus n, but it's secretly 5 squared minus 5, as you can see. And if you remove 1 row or 1 column, the dimensions would be 4 by 5 or 5 by 4, and you have this previous proof around factoring.
In the chat, we have another suggestion.
Yeah, what's the other suggestion?
Cameron suggests deleting the diagonal.
Yeah, so the idea, I don't want to put the idea aside. The idea absolutely works. And let's extract a new idea, a second idea, which is attributed to Cameron via chat, which is to remove the diagonal. Okay. Yeah. Now, why does this work? It is true that this somehow proves it, but like, why?
I like this
I
one because it
noticed.
just leaves the symmetry in.
Yeah, I'm hearing multiple voices, and I see the symmetry. The symmetry of what though? Like, what is it? How can I think if I present this?
The triangles that are left over, like the upper one and the lower one, are the same size as each other. So we got like 2 triangles.
Yeah, you got 2 groups of the same size. If you got 2 copies of this thing, it's got to be even. 2 times anything is even. 2 times any whole number is even. So 2 times the dots at the top or the dots at the bottom, it's even. I don't know.
So I have a question, Benjamin. That made sense to me with the array model, but I just did an area. So taking out the diagonal, I can't make meaning of that for area. So I like it. I agree. It gives me 2 of something, which I love, but can you take away the diagonal and have an area meaning for that?
I'm going to try to draw the same thing with an area model, but I'm going to just do 4 by 4. I don't think I have another 5 by 5 in me. So I'm going to do my best. So here is something that has area 16 because its dimensions are 4 by 4, which in particular means I divide it in half one way and divide it in half the other way. The area of this right now is 16 square units. So if we decided that we were going to remove 4 square units from it, and if we took Cameron's same idea from the chat, which is to remove them along the diagonal, each of these x's is removing 1 square unit, right? And so the remaining area is again in these square units symmetrically distributed with the same idea that Kate and TJ had mentioned moments ago, right? So I don't know if that answers your question sufficiently, but I hope the same idea works. Okay. So we have this nice phenomenon that we could have used the original idea, which is to remove a row or column and gone back to the second proof. One thing that you might think about, but this is the kind of thing where you don't shout it out, is like algebraically, what does removing the diagonal correspond to? I think there's probably room to write a book called Thinking Diagonally. I don't know what would go in it, but if you write that book, I don't know, get me some royalties. Okay. The next proof that I got in mind is one that requires some prerequisite knowledge. And maybe you have it, in which case this will go along smoothly, and maybe you don't have it, in which case it will be less smooth. Does anybody happen to know, if you add up the numbers 1, 2, 3, all the way to, let's go to n-1. Does anyone know what you get? This is an arithmetic series where the common difference is 1. What is this total? Someone will have to just
N
yell.
times n minus 1 over 2.
Yeah, n times n-1 over 2. And I'm even going to expand the numerator to n squared minus n over 2 because that's what we started with. This is a new idea, I think, for some. Maybe for professors of mathematics, this is not a new idea. But if the left-hand side, meaning the thing we started with, I'll underline so you know what I mean by the left-hand side. If this thing, which is a sum of integers and therefore itself an integer, is equal to this thing, the numerator of that fraction better be even, right? If the numerator were odd, if it were like 13, then 13 divided by 2 would be 6.5. There's no good. We can't have that 0.5 lingering around. So if you can associate an integer with an expression divided by 2, then the expression has to be even. So we have here like a proof by arithmetic series. The other thing we have here,
I
and
like
maybe-
really want to take the 2 and like multiply it
yeah,
over to the other side,
not only will we do that,
just desperately.
so we will avoid a math talk that involves desperation. Yes,
Thank you.
a good goal in general. Okay,
Always.
usually. Yeah, right, always. Okay, so here we have very literally n squared minus n is equal to 2 times this sum. Now, if you thought ahead a moment ago, maybe you know the left-hand side. That left-hand side, which is 2 times the n minus first triangular number or whatever you want to call it, that's actually the previous picture, right? If you go back and re-examine these. 2 times, well, let's see. In this case, if we make n equal to 5 in green, it's 2 times 1 plus 2 plus 3 plus 4, right? And so actually our picture from a moment ago, here's the 1 plus 2 plus 3 plus 4 in the picture, and then we have a second copy of it. That was the whole point of this proof, right? Circle them individually. But actually this idea of an arithmetic series here is somehow capturing the geometric representation from number 3. So we could have gone with the original idea of a row or column, and we would have gone back to number 2. And if you're wondering, what does it mean to remove the diagonal? Well, get the idea in number 4, arithmetic series. Okay, let's do, that's 4 proofs, by the way. I've said 7, so let's see if we can get to 7. Okay, 5. If you have a group, well, I should not say this to mathematicians. If you have n people, and you want to make committees of size 2. Now, I'm not sure how to spell committees, so I'm going to write CMTE, committees of size 2. And how many ways can you do this? You know, this is sometimes denoted as n, and then choose 2 of them. Does anybody know offhand? How many choices do you have for the first person?
N.
That's right. And after you've chosen them, how many choices do you have for the next person?
N minus 1, because you can't be on a committee with yourself.
That is right. Not if we want them to have exactly the size 2. Sounds like it's like a Groucho Marx joke or something. I don't know. Now, if you have person A chosen and then person B chosen, this method also would have person B chosen and person A chosen. We're double counting. So we need to divide by 2 to make sure we're keeping things honest. And again, I hope no one will object if I multiply the numerator n squared minus n divided by 2. And this is the same idea of associating, I'm going to use big words, algebraic information with combinatorial information, right? If you have here underlined in orange, in the future tense, what's got to be an integer, then you have here this fraction, expression over 2, the numerator has got to be divisible by 2. Unless it causes any despair, let me just multiply both sides by 2, just for the sake of those who feel that particular motion. 2 times n choose 2 is n squared minus n. And so indeed, since this is an integer, we have n squared minus n being an integer as desired.
Great, I have a question.
Yeah.
So this is the proof I know of the result you used in question 4, or in proof 4. So this one feels a little like cheating. Do you have a sort of a separate way that you think of the result from 4 that doesn't rely on this?
From my perspective, if you ask me to prove the identity in number 4, I'm not sure that I would use this particular way. I would use maybe one of the tricks around adding up 1 through n minus 1, like a rewriting it in reverse order.
Okay.
Or
induction or something like that. Great.
Yeah. And I would say in some sense, a person could say about all these proofs, aren't they exactly the same? If I said to you, I added up the numbers 1 through n minus 1, what did you do? And you said, I was thinking about how many committees of size 2 I can make. I would say, well, we're probably doing something that feels different to me. On the other hand, if you can prove that what I'm doing in 4 and 5 are the same thing, then you do indeed establish that identity. So instead of the objection to maybe we're relying the identity, if we view them differently, then in fact, we can prove that they're the same.
Mm-hmm.
I hope that addresses or sufficiently evades the question. Okay.
Yes.
That's 5. So I think we're doing pretty well. How many things do you prove in 5 ways? I don't know. Okay, 6. This is going to be maybe the first time that I start to use terms that are not familiar. I'm going to use the principle of mathematical induction, right? Because this is a question about natural numbers, and often when you have a question about natural numbers, induction comes up. If you have never seen the principle of mathematical induction before, my recommendation is not to try and learn it from what I'm about to say. If you've seen it before, then probably you know everything that's going to happen, and you will be bored. So nobody will win with this proof, but let's just do it because I promised 7 and I only have 6 otherwise. Okay, principle of mathematical induction, and I think I'm spelling principle right. principle of mathematical induction. By the way, a person who's thinking about what does it really count, what does it really mean to have two proofs that are different? There is an equivalence between principle of mathematical induction and the well-ordering principle. My seventh proof is not using the well-ordering principle. And so if you want to try to think about how would you use that to prove this, I welcome you to do so. Maybe we have 8 proofs for a future talk. Okay. So here what you do, there's 3 parts of a proof by mathematical induction, right? There's the base case, the inductive hypothesis, and then there's the k+1 case is how I'm going to refer to it based on my notation. And again, if you have not seen induction before, I don't know, just let yourself drift in and out for the next few moments. So here's the base case. Okay, base case. Base case here, because they're positive integers, is when n equals 1. And then we have 1 squared minus 1, which is 0, is even. Fantastic. If you're presenting this to students, do not be surprised, even if they know mathematical induction very well, if someone raises their hand or just screams at the top of their lungs, 0 isn't even. Just a warning, and maybe some of you know this from your own experience. That does happen. Be prepared to go way off on that. Maybe if you say is 4 even, subtract 2, is it still even? Is it still even? If you say, but 0 is a multiple of 2, it's 2 times 0. You think this is convincing until you try to convince someone with it. Anyway, okay. The next part is the inductive hypothesis. I write it as IH, which is an interesting pair of letters, because if you turn your head sideways, it still says IH. Anyway, yeah. Suppose k squared minus k is even. And here I'm not writing in every single word. K in this case is a positive integer. You know, k is not pi or something like that, but it might even work anyway. And so that's why I use the k+1 as the notation, k+1 case. We're going to try to use the supposition in the inductive hypothesis to prove that when n equals k+1, that this is true. In other words, when n equals k+1, we have n squared minus n minus n. Oh, well, what is this? K+1 squared is k squared plus 2k plus 1. And then we subtract this off, we have minus k minus 1. And that's k squared. The 2k minus the k is just plus k. And the 1 minus the 1 was gone. And the idea here is to use our inductive hypothesis, right? So let's take that inductive hypothesis. And we can just note that to get from k squared minus k to k squared plus k, we just add a 2k to the end, right? And now we're in a good situation because this is even. That was our inductive hypothesis. And this is absolutely even, right? Because it's 2 times the integer. And then as Tian said at the very beginning, we're going to take it as known knowledge that the sum of 2 evens is itself even. And again, it's like a gotcha. We're done. If you don't know that the sum of 2 evens is even, this principle of mathematical induction must be very confusing. Okay, good. Good. Oops. If you were going to write this out in full language, maybe you'd say, therefore, by the principle of mathematical induction, the statement holds for all positive integers n greater than or equal to 1. But I'm not going to write any of that, actually, at all. I said 7 proofs. Evidently, I've written the 7. I'm going to hold off on this one for the moment. Something that I find very fascinating, I'm going to switch to colors for dramatic effect.
Dun, dun, dun.
Yeah, can you feel like, what could it be? Unless you noticed me with the palette just now. Yeah, it's going to be pink. Something that fascinates me about this question is that there are at least 2 ways of representing it. There's really a third, but maybe I won't get into it too deeply. The original question says that like n, get the pen feature, n squared minus n is even. And remember, even means is a multiple of 2. Throughout our first 6 proofs, we used at least 3 times, I think, the identity n squared minus n is equal to n minus 1 times n. And so you could similarly say that like n minus 1 times n, and then the same thing, is a multiple, I don't know if people still do this. Those 2 lines mean exactly what's above it, is a multiple of I'll write the 2 again anyway. These are equivalent statements, but because they are represented differently, if you try to generalize them, you may end up with different generalizations. Yeah. So again, dramatic effect, we try to switch colors. Let's try, I don't know what to call this, plum maybe. If you're asking me how to generalize this, well, we can't just replace n with a different letter, but we can replace the number with a letter. Maybe the first line says n to the k minus n is a multiple of k, is a multiple of k. And maybe the second one, oh, I won't write them all down, but that's 2 numbers in a row. So maybe k numbers in a row, k consecutive integers or naturals or positive integers have a product divisible by 2. A product divisible by 2. Again, there's, when I say there's a third way of thinking about this, some of you may think, well, actually this 2 right here, we could rewrite it in a slightly different form as 2 factorial. And then maybe that would give us a slightly different representation. This, of course, thank you for nobody screaming over me, GDK. And so maybe you would end up with something different if you use that factorial representation. We'll avoid that. And so if you're asking me, which you are not, how would I approach these 2 different statements? I'd be like, well, the number after 2 is 3. And I would check, is it true? Let's see if we can do any damage to this. So n cubed, oops, is n cubed minus n a multiple of 3? A multiple of 3? And the other version of it, again, if we start at n minus 1 and then we have an n, now we have a third term, so n plus 1. Is this a multiple of 3? And so how are we going to approach this? Well, in the latter case, well, I don't know, we can do either one. Maybe we'll do the former case. Let's do the latter case. The latter case is 3 numbers in a row. If you have 3 consecutive integers, one of them is a multiple of 3. I hope you will just trust me on this, if you do not already know it. If you have 2 numbers in a row, we use that fact way up. One of them's got to be even, in other words, a multiple of 2. Otherwise, 3 in a row has got to be a multiple of 3. So the whole product is a multiple of 3. So like the second statement is definitely true. The first statement, well, it just so happens n cubed minus n, if you factor an n out, this time factoring on the left, is n squared minus 1. And we know n squared minus 1 is equal to n minus 1 times n plus 1. Let's not lose the n. So actually the 2 statements here, despite their generalization, are equivalent. So they're both true. And maybe you'll think, okay, it doesn't really matter how we phrase it. We generalize and we prove them both. But you will run into trouble shortly thereafter, right? Because if you take the next case, n to the 4th minus n, is this a multiple of 4? And right, we're asking this about all counting numbers n. And you can see, if you plug in 0, which is not even a positive integer, but okay, that's a multiple of 4. 1 minus 1, again, it's a multiple of 4. But if you plug in 2 to the 4th minus 2, 2, 4, 8, 16 minus 2 is 14. Oh no, it's not a multiple of 4. Whereas if you look at the second generalization, this one here, if you multiply 4 numbers in a row, it will undoubtedly be a multiple of 4. And so this leads to a question, which I think is nice for people who are undergraduates and looking for a theorem that could be of some use at some point in their life. When is it true? Is it true that n to the k minus n is a multiple of k? And if you have taken a course on what's called elementary number theory, not because it's an elementary school, but because it's an early version that has no complex analysis inside of it, then you know that for k greater than 1, this is true at the primes. In other words, there's a reason that this was true when k was 2 and when k was 3, but not when k was 4. 2 is prime, 3 is prime, and 4 is not. It's true again at 5. Okay, I said I would give a 7th method. The name of this, in some version, is called Fermat's little theorem. Fermat's little theorem. Fermat, very irritatingly, has 2 famous theorems named after him, and they're both abbreviated as FLT. So I will try to using a miniature L to denote this way up. I said I would give 7, right? Okay, this is in fact Fermat's little theorem with the prime 2. In particular, that n squared minus n is a multiple of 2. In other words, even if you were to give this question to someone and they were to tell you, of course it's true, it's an instance of Fermat's little theorem, I think it would be somewhat shocking. I think that about takes us to the end. I promised to give 7 different proofs. That's 7. I didn't do the well-ordering principle. There are some other ones that exist out there. I recently had a student send me a message and say, this whole n squared minus n thing, I'm pretty sure we like covered that in Algebra 2 class. And I started to think about things we had covered, and I noticed that if you are careful about it, if you start to add up the first few evens, like 0 plus 2 plus 4 plus 6, in this case you would get 12, which is equal to 4 squared minus 4. So if you take these 4 even numbers starting with 0, there's another idea lurking here, and then there's also the well-ordering principle. Again, I have not written this out. I would challenge any of you to come up with another truly distinct proof, but that's probably what I got for this time period. You're welcome to ask any questions. I see 95 missed items in the chat. Great.
Thank you. So Benjamin, why multiple proofs? Either you particularly, or if you want to talk about the culture of mathematics to value this, or yeah.
I think, well, okay, you just want me to pontificate. This is the part that doesn't get uploaded to YouTube, right? I think for me, much of the interest in mathematics is not necessarily knowing the validity of the outcome, but actually what the method is. I have a dream of a type of math class, which I'm not prepared to teach, and maybe one of you is, that begins with a statement, elicits multiple proofs, and then has students use the different proof techniques to pose new problems. And then you'd be building off an initial proposition. You would take the student methods and then have them asking questions, which I also think is an important part of doing math, to move the class forwards. And you would see if you could get from an initial proposition to the different proof types. And then from there, can you pose different problems and then iterate on this sequence? This is the dream. I'm sure many of you have had the same dream. I'm not yet sure how to do it. Maybe I'll just mention briefly. I have a problem that I think could work for that. It's a different problem than this, although you can see if you're teaching a class in high school, as I teach classes, or if you're teaching a class to undergraduates, if you're covering, I don't know, factoring, parity, modular arithmetic, combinatorics, proof by induction, and up to Fermat's little theorem and geometric representation, I think probably it's going to be an okay class, at least on paper. There's this famous question of like, if you have a bunch of matchsticks, maybe I should draw them as matchsticks. If you have a square array of matchsticks, how many are there? And I just really like this question. And I'm convinced morally, as mathematicians often seem to say, that there's a way to prove this in a bunch of different ways. And then you could then expand in the different ways in proposing new problems. So like one way to prove this is that how many vertical and how many horizontals are there? There's like a cases proof. Another way to prove this is by saying you could do it by the principle of mathematical induction. Another way is to introduce this v minus e plus f equals 2 idea. Personally, if you ask me how I do this, I have for many years put an L in every one of the cells. So here's an L and an L and an L. So in every one of these n squared, and it's 3 by 3 here, but in every one of these n squared cells, there are 2 matchsticks drawn. So there's 2 times n squared total. And then you're missing the n along the top and the n along the side, so plus another 2n. So this really quickly shows you how to count in a square of dimensions n by n made of matchsticks, how many edges are there? I don't know, I personally call it L counting. I'll keep it in red, because this is not a term used elsewhere. But I've wondered for a while, what are the other interesting L counting problems you can do? I often tell students that there are 2 rules of counting. Don't overcount and don't undercount. I've recently added a third rule so that students don't try to get around it. The third rule is count, because it turned out some were just not doing anything at all. And they were satisfying the first 2 principles. I don't know if that totally avoided your question. because seeing things in multiple ways is cool and gives new insights, and maybe you can connect different techniques, or, you know. Yeah, are there other questions or complaints?
I have a question, because you and I were part of a Twitter conversation about the divisibility by 7. So since you have time, I wonder if you have one proof of the divisibility by 7 as opposed to the 7 proofs you did about the evenness problem.
Ooh. Yeah, there was that. It is true that there is a inside of Twitter. This is my dream one day that you interact with people in real life. I suppose this is real life, but physically, and you reference an old Twitter thread about divisibility rules. I can say, oh, remember when I tweeted in September of 2018 about dividing things by 7? I appreciate your question, and I'm gonna answer a question you didn't ask instead, which is, hey, we did this for 2 examples, n to the second, n to the third, and showed it failed at n to the fourth. You said it was going to be true for primes in general. I hear you asking about the number 7. How hard would it really be to prove without Fermat's little theorem that n to the 7th minus n is a multiple of 7? I think this is probably what, you know, if someone were to say, what would be the sort of question you could ask a student afterwards for? To me, I think this is a very nice question. Divisibility by 7, again, you can use modular arithmetic. I think there's something about something, peel off the last digit in the ones place and then do something or another like that. But I think this, to connect the idea of 7 and its, I don't know, omnipresence with this actual talk, if this here, and I'm not going to go through it, but if you factor out the n, you have a difference of cubes and a sum of cubes, each of which factor, right? And then you end up with this nice situation where you don't have that much to check. Because if you do that, you'll have n here. This will be n minus 1 times some other stuff, and this will be n plus 1 times some other stuff. And so here, a number that's 0 mod 7, a number that's 1 mod 7, and a number that's 6 mod 7. Those 3 are taken care of, and these will each knock off 2 more. And if I'm speaking too quickly about this modular arithmetic part, sorry. Yeah, I think this is probably a good proof. If I were going to make this the homework assignment, I would probably have gone through more carefully the case of n to the 5th minus n, which again, n times n squared, sorry, n times n to the 4th minus 1 is n times n squared minus 1 times n squared plus 1. You end up getting a bunch of nice factors, 3 of which take out 3 cases, and the last one takes up the last 2. So I hope again that I've sufficiently answered, but actually evaded your question. But I did mention 7 in the response. Are there other questions or critiques?
Are you familiar with the book 99 Proofs? I don't know if that's the exact title. Came out, I think, last year.
No,
let me grab it so I can give you the exact title, but because it's wonderful.
99 Variations on the Proof by Ording.
All right, I'll look into it.
Yeah.
Now that you mentioned a book, I should mention also a book. Now I would use the, yeah. Oh, hold on. This is the book by Joel David Hampkins. Yeah, I think it's backwards in my screen, but I hope it's forwards in yours. If you ever get your hands on this book, which I don't know if you want to buy it. I don't know if you know if he's on this call. If he is, you definitely want to buy it. If he's not, whatever. Chapter 1 is an introduction, but chapter 2 is exactly the content of this talk and is indeed attributed to me. I think it's pretty cool that this, like, either a professor somewhere, Oxford.
What's the title of that again?
This is called Proof in the Art of Mathematics. And its entire second chapter is basically my answer to that math overflow question from the beginning. And then it's also written up inside of a journal article in the now defunct mathematics teacher for the NCTM. I'll try to tweet out screenshots of this talk afterwards, and I will put a link to the NCTM article in there.
This is you probably can't see it.
Turn your virtual background off.
Yeah. It's called 99 Variations on a Proof by Philip Ording. And it's wonderful. Each one of the proofs has a discussion of it. And you have all these different variations. So it's a lot about how do you communicate mathematics? How do you prove things? Some of the proofs involve things like the proof is left to the student, but there's a discussion about that. So it's very clever. Some of them are screenplays, some of them are standard proofs. It's a lot of fun. I was just enjoying it so much. I limited myself to just reading just one proof a day. So I recommend that by Ording.
it is true that in the 7 proofs, I mentioned there's a sum of evens proof and then there's a well-ordering principle proof, but I don't have proof by screenplay on my to-do list. I didn't. I suppose now maybe I will. Yeah, proof by screenplay.
What about proof by contradiction? I tried to do it, but it seemed to collapse into one of the other techniques.
That's the same concern that I would have. Suppose that it's odd, and then how do you avoid just having the algebraic manipulation? Or if you try to represent it geometrically, yeah. I'll have to think about that because that's at least worth including in a discussion of proof techniques, proof by contradiction. Yeah, should make a note of that.
Is there a version of this proof that involves assuming the Riemann hypothesis is true? Sorry, Dave, did you have a question?
Oh, it's not. I mean, you started the talk with this math overflow post, and I expected you to circle back around to it. I feel like I missed the punchline.
This answer exists as a post on Math Overflow. I grew significantly disillusioned with that particular post, and so I put up my own answer to that post, which I can share my screen. I think on this post. Where is this thing? Oh yeah, elementary plus short was useful. Also, like, while we're at it, shout out to whoever. I don't know. I'm not inside of an account right now, but there's like 3 downvotes on this. Who downloads this post? Whatever. You can see the celerity with which it proceeds. Cases, high school algebra, number theory, arithmetic, geometry, common works, induction. This is actually the original place, unsurprising to those of you who are familiar with MO, Math Overflow. This is where Joel David Hankins originally saw this. And indeed, you can see much of the content from here and including from my stuff there. So if you're wondering what is the loop back, is that from my perspective, if you tell me I have 30 minutes with undergraduates, this is the sort of thing that I'd be talking about rather than, oh, I don't know, something that, like, I don't know, a completeness theorem, like not using a completeness theorem, using I don't know, what is it, ultra products, right? So hopefully that answers that question. Yeah, are there other rants?
So to bring things back to the question about proof by contradiction, the natural way to prove this by well ordering would be a proof by contradiction. Suppose there is, an n such that n squared minus n is an odd, and then use the well ordering. There's a minimal one, and then you get a contradiction.
Yeah, I'm gonna try to write down what you just said, and you tell me if I'm misrepresenting what you said. So you're saying that maybe if we actually try this, like, this could be where the proof of contradiction is hiding. Proof by contradiction, right? The well ordering principle says that if you have a subset of the counting numbers, we'll say, that's non-empty, it has a least element. And so we'll say, suppose that there were an n for which n squared minus n is odd, and then there would have to be at least such n, and perhaps you could go to its predecessor and show it.
And then it would just be the induction argument there, and you get a contradiction at the end.
Yes. Okay. I had thought that maybe it was not worth doing this because it's too similar. Induction, but I think you've convinced me otherwise. In very few words, you'd probably have to put in maybe an extra piece because you'd have to say either its predecessor, it was true for its predecessor, or you'd have to check by hand that it's not true for one.
Yeah, I guess you'd have to check the base case separately.
Yeah. So there's the answer. We have gone through the rants.
You don't have to go all the way to the base case. Suppose that you have the least such where it is not even, then you go from there to the one below it. If it is odd, the one below it is odd, but it was the least, so that's immediately contradiction.
Good. I feel that we have converged to an 8th proof. Maybe this is false advertising. I only promised, well, I said 7. I don't know if you say I have 7 proofs and you give 8. Is the claim still true? I did not say exactly.
Yes. I believe in hierarchical inclusion, so.
Yeah, right. This is, yes, we are counting numbers. Yes. Hierarchical inclusion is a good term. Are there other comments? I heard the Riemann hypothesis.
I've got something for you, Ben, which is just the talk made me curious. If you've thought about this before, I don't know. but what would be the lowest tech proof of Fermat's little theorem? Like, I think of it in terms of group theory, but I'm sure that Fermat didn't think of it that way. So maybe that, yeah, go ahead.
If you're asking me how do I prove it, I will say like, do the little thing with the thing and then use Lagrange's theorem and then the power and it gets back to the one, multiply both sides and you're good to go. And if you are speaking in the idea at the beginning, which is to avoid a situation of what I think constitutes meanness, then Lagrange is not going to be a good method. In the article that's cited in Hampkin's book, I did put in an appendix 2 things. One, full case by hand that n to the 5th minus n is divisible by 5, because it's just not that difficult to do. And 2, I did put in a proof of Fermat's little theorem that involves multiplying a bunch of numbers together and then seeing which things reappear, and you have some factorials, but it does not require any group theory at all. So I think it's basically a pointer to the article, which again, I'll tweet out a link to this. It's at the very end, and it's not intended for the general audience. It's intended for the strange situation in which some years later I would give a talk and have the exact question from someone with a great first name.
Thank you.
I don't have much to say about the Roma hypothesis in this context. There's no inaccessible cardinals or ultra products that are in here. Are there any other questions or deep complaints?
One compliment. If
Yeah.
my number theory classes when I was in undergrad had been taught this way, I would have had a lot fewer headaches.
One thing, the response to a compliment is a rant, right? One thing that irritates me is how much young people love number theory. You ever talk with like high school students, elementary school students? In elementary school, it actually is in there with least common multiples and greatest common factors. The fact that there's not more number theory in high school is so irritating to me, because it's like, no, you gotta like learn synthetic division, because it's gotta like someday you're gonna be doing integral by hand. The last term is gonna like end up being, I don't know, inverse tangents. I cannot defend the division of polynomials for all students in algebra 2 classes or whenever, or obscure trig identities. Whereas I am convinced that if we gave more students an opportunity to see number theory early on, rather than this prolonged calculus sequence, that we'd have people who have not only would be more likely to pursue mathematics in a post-secondary context, but also would have a better idea of what post-secondary math looks like beyond the calculus sequence. So I agree with your comments about teaching early number theory, but also I would like to pull that number theory back even further. I'm so irritated that like making like least common multiple and greatest common factor on their own are the source of wonderful problems. Like if you say, okay, here are 2 numbers with this least common multiple, A and B have this least common multiple and this greatest common factor, find all solution sets for A and B. Already you have a rich problem task that can be explored starting at the elementary grades.
Benjamin, do you have a good source of number theory problems for K-12 or accessible to high school kids?
Yes, so instead of referencing a single tweet, it turns out some years ago, I along with my coworker, Liz Brennan, she and I taught a mini course through Math for America about the times table. And we have put all of our materials, we taught 3 consecutive classes, mini courses on problem posing. The one about the times table is secretly about number theory. So I will provide that resource as well. Everything I've ever made is free for you to use and hopefully improve on.
Great, thanks.
I think there's good stuff in there. It starts out with this question. It says like, what's the sum of an n by n multiplication table? And then it says, how many distinct numbers are there in an n by n multiplication table? And a lot of people secondary school teachers and those who are math majors can answer the first question, but actually the second question, how many distinct numbers are in an n by n times table? Not so hard to say. Some people are amused that the 10 by 10 table, I think, has 42 different numbers. Some people seem to like this 42 numbers. But figuring out a general formula is way too hard. You should not assign this. And for me, it is an instantiation of one of the ways in which number theory is an area where it's pretty easy to ask a question that's really, really hard to solve. And I think that's one of the reasons that some people are hesitant to broach it at all with younger students, because students can easily ask you a question, and then as the teacher, if you're expecting that you'll always have the answer, you might not. So hopefully, again, I have answered or evaded the question. I think this one I answered. Yeah, that resource.
Perfect. Thank you. So as we wrap up, our next week's speaker is here. Kim, would you like to give us a 30-second foreshadow of what you're going to be talking about? Oh, might have frozen Kim. Well, the algebraic units that pretend to be squares is the title. So you can see the title here. Everyone is welcome to join us every week. We hope you will. And this talk and most of our talks go up on YouTube afterwards. So feel free to share this, especially with the high schoolers in your lives. And let's please join me in thanking Benjamin one more time for this session. Excellent, thank you.
Benjamin, one of the things that when you mentioned your dream class about this proof idea, which I thought was really cool, another resource that I have but not here presently, there's a book called Crossing the River with Dogs. I don't know if any of you guys are familiar with this book, but it's a book of problems sorted by how you solve them, like what type of strategy you use. So like there's a chapter that's called drawing diagrams, and all of the problems in that chapter are not related to each other, but they're each helped by drawing diagrams. And then they have, another one about guess and check. So there's a guess and check chapter where all of those sort of random assortment of problems are approached by that strategy. But it's a really good resource, especially if you're teaching, a problem solving class and want to, go and find some cool things that are linked together in that type of way.
You're telling me that after I give a talk and now I have to read 2 books. I have to read the 99 Proofs book, and now I got to read about canines and canoes, as I've now already renamed the book.
That's right. That's right.
That sounds wonderful.
The thing is, it's expensive. The book is expensive. So
oh, no,
that's
I will, is it recording? I won't find a PDF online.
No.
There is a paperback version for $24 on Amazon.
Oh, that's good.
Pausing the recording now. Bye.
Sorry for the crash.
It's all right. Kim, you want to tell us about yours?
Okay, well, I'm hoping not to make the grand mistake of being incomprehensible, as we've well been warned against in this talk, but I'll be continuing with the theme of number theory and trying to introduce my favorite object, which are units of number fields that look like they should be squares, but aren't.
Great. Thank you.